well, sir. What seems to be the problem?
I have like some neck pains and like a pain in my head. It hurts a lot.
Let me check it out. I think we're going to have to administer an angiography test. Let me get everything ready. You wouldn't happen to be allergic to iodine, would you?
I don't think so.
It's not going to hurt that much. I'm going to turn on the heart monitor just to make sure. Beep. 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 Beep.
The scene you just finished watching was a dramatized version of the original angiography at the onset of the 20th century. The angiography came about with the discovery of the X-ray. In order to produce an image of the blood vessels, iodine would be administered to the patient through a syringe directly at the neck. Unfortunately, the iodine being toxic often led to death, and only one side of the brain could be angiographed at a time. They hoped to fix this issue by using a catheter rather than a syringe. The catheter allowed for the increased mobility of what could be angiographed, that now included the heart and neck, and it allowed for both sides of the brain to be pictured. Basically, the catheter would be a tube placed within a piercing on the upper leg, which allowed for the contrasting agent to travel through major arteries and veins to the heart or brain. The catheter ended up ineffective as well, because too many deaths occurred due to extreme blood loss, stroke, and allergic reactions to the contrasting agent. The later 20th century allowed for the use of a less toxic contrasting agent with magnetic resonance imaging. This eventually led to the disappearance of the dye, to where the magnetic resonance imaging scan could take a picture of the neck and brain by only using the different tissues in the blood vessels as a resource. The MRI today is used through employing two different techniques involving the way in which the subatomic spins affecting the detection and creation of an NMR, nuclear magnetic resonance signal. NMR is basically the detection of the photons released from an atom when transitioning from an excited to ground state. Long before the modern MRI, Dr. Charles J. Singer observed the primary phenomena of the first method. The method is dependent upon the displacement of longitudinal magnetization. Longitudinal magnetization is the vector of net magnetization in the direction of the constant magnetic field. The second method involves the use of a change in the magnetic spin that was first observed by Dr. Dietbert Hahn in 1960. Now Max will discuss the physics behind the MRA.
So to understand today's use of the MRA, we have to understand three equations. The first of which is the integral of the bipolar gradient multiplied by the distance multiplied by the time, when time is 0, should equal 0. That's explained by this equation. The bipolar gradient is nothing more than something that takes the form of a balloon shape in the x and y axis. So the bipolar gradient of 2 would look nothing more than something like this, where the total area within the bipolar gradient goes up to 2, and it takes the same amount of area and the negative and positive side of the x and y axis. Once we understand that equation, we can get into a more difficult equation where the charge of the spin of the particles should equal the Lamar frequency, which is a constant, multiplied by the velocity in the x, y, or z direction, multiplied by the distance, or multiplied by the difference of masses. And because the integral allows us to find the difference between two masses, that is what's given to us in the first equation. So once we are able to understand the mass, we have to solve for the Lamar frequency, which is equal to this. What this means is that it's the charge multiplied by gravity multiplied by electron field all over twice the mass. Once you're able to understand those two variables, we can go back to our second equation, which is the charge of the particles multiplied by Lamar frequency multiplied by the velocity in the x direction times the mass. So we know what this is. We know what this is, and we know what this is because it's given to us in our use of the MRA. We can solve for the velocity, and the velocity, because we can only do it in one direction, we have to do it for the x, y, and z direction to get the full velocity and the full blood movement of every single of the entire blood vessel.
Thanks, Max. Now on to the big question: what are MRAs used for? Nowadays, doctors use both X-rays and ultrasonic imaging to visualize vascular diseases, but neither one works quite as well as the MRA. X-rays use a liquid which allows blood vessels to be picked out of an X-ray. Unfortunately, the liquid is sometimes toxic and can lead to bad reactions in patients. Ultrasonic imaging isn't as risky as X-rays, but it's also not as effective. With ultrasonic imaging, a doctor can't view the vessels that are covered by bone or that are deep inside the body. This keeps doctors from using them to diagnose things like neurological problems, which, as we'll see, is one of the most common uses of the MRA. Ultrasonic imaging is also entirely dependent on the operator's skill, making misdiagnosis very common. The MRA also goes beyond what either of these are capable of. With the MRA, doctors are able to view small arteries that are often difficult or impossible to view through other methods of imaging. MRAs also allow doctors to judge both the velocity and the amount of blood flow in a given artery, leading to improved evaluation of neurological diseases. The MRA is, however, still not perfect. Although the tracking agent is not as harmful as the one used in the X-ray, it's still possible to have an adverse reaction. The agent is also expensive. The use of more powerful magnets in the MRA has led to the use of less and less of the agent, and the hope is that eventually none will be needed at all. There have also been advances towards making these machines able to diagnose things themselves, entirely eliminating the possibility for human error.